So I'm sorry, guys. Things have gotten worse for my dad. And anyway, I didn't get a chance to record this last night when I got in. There was a lot I had to do. Anyway, so I'm recording now. It's about 3:29. I'll get this posted and then we'll meet at 6 o'clock. And what I'd like to do is we're just going to walk through your assignment, the pros where assignment, and do it together. So we probably won't take the whole hour and a half. Hopefully that'll be okay with you. And we'll pick up next Tuesday and continue on with our last 2 weeks. Like I said, I apologize. I've never had to do all this in this amount of time that's come about, but it's the way it is. Anyway, so I'm going to continue on. I'm not going to play the videos per se because I don't want to waste time doing that. I'd rather talk about these things. And again, the presentations are there for you the entire time of our course together, so you can always refer back to them. And I would suggest looking if you need more in-depth information pertaining to some of these things that we're talking about. That's why I put them in the presentations. And I haven't forgotten about you, Isaiah, about regarding the CompTIA Network Plus things to look for. I have provided in the folder the objectives. I've provided Professor Messer. You should really watch him and look at those areas that he goes over in the exam, the CompTIA Network Plus 008 exam. He's really good, and that will help you. Other than that, I don't have a lot more than other than the 2 mock exams we're going to do together. Not next week, but the week after that, Wednesday and Thursday night, you'll have 2 mock exams of CompTIA. And then I would practice doing your TestOut practice exam over and over. And what they've provided you for the pro and for the CompTIA as practice exams. All right, so we were talking about switch ports. So we talked a little bit about link aggregation. We talked about trunking and VLANs. And remember, the practice of bundling, and these are all the things that I write here that I put to try to explain things the best that I can, well, without physically doing these things. But when you bundle together, you have much better performance. I mean, think about it. Whenever you have something singularly, you know that it's taking up more of the bandwidth, the space, the having numerous things that you have to consider. When you bundle something together, it makes it a bit better and it flows better. So the semantics here can vary. Insiders talk about similar practices like port trunking or link bundling and ways that a cloud can do a particular thing, right? So when we look at LACPD, which is Link Aggregation Control Protocol, which you're never going to remember all of these things, which is why I always have my students in my networking class do I give them all of the acronyms and they have to supply the definitions for them and keep that sheet as you go through your career working in networking until you start doing all this. But you're not planning to be in networking per se, but you have to understand networking in order to do securing the security part of it, right? So we're looking at the protocol of 802.3AD when we're talking about link aggregation. So the experts have referred to the group of these ports as link aggregation groups, and they are labeled as such. So always remember that, link aggregation. Now, some of the things, and I know it's a lot on one screen, but some of the things that we think about, I always like to look for what are the best practices? What are some of the examples of these things? So the major importance of what the link, not aggravation, I love that, I put aggravation. Oh, I love predictive text. It can't be aggravating. It can't be aggravating. So aggregation, what does it do? Well, it's redundant, right? Suppose you had a single link and that link fails. Not a good thing, all right? Because you lose 100% of that connectivity. You just go dark, right? You're done. With link aggregation, you have the ability of multiple paths of delivery, right? The ability to load balance. If something is too busy, like when we talk about servers, we have a number of them, we load balance it. This one's way inundated with requests and queries, well, then we're going to jump to this one. Well, the same thing here. It's like I told you when I was doing student housing on my campus. I ran duplicate lines for redundancy of Ethernet cabling between houses in case one of those cables crapped out on me. It didn't stop students from having connectivity. I would just have the second one to take over when then I would repair or replace that particular one that crapped out on me. Well, it's the same thing here in everything that we do in networking. You want to have multiple paths. You want to keep people going. Plan B, plan C, plan D. So the ability is to load balance. And again, using the same link for each related packet is still going to be the best practice. Also, making sure that all related data packets go through the same individual link solves potential problems with those that we don't always receive all the data in order, right? So link aggregation will address this. Also, the bundling leads to much more durable signal in our interfaces. Also, the promise of graceful degradation. In other words, a failure, if it's going to happen, it's not stark, it's slowly, gradually happening, so that you need to pay a little attention to that performance, but at least you can finish what you're doing and then go and repair that issue. And instead of cutting off a signal, it might only initially suffer a very small bit of degradation, giving the end user, or we call them stakeholders, time to react and diagnose the product and address it as it's occurring and not waiting till it happens, right? And various link aggregation configuration guidelines help us to optimize how link aggregation protects our networking data and the performance of our network. And with that in mind, it also promotes the formation of better logical virtual links or bundles that can be handled in one unified whole by a Mac client. I believe I might sneeze, so I'm going to pause this. Maybe not. Pardon. All right. The benefits. So continuing on. Again, the bundling offers system designers and administrators new ways to address points of failure. Excuse me. So you want to have that. Points of failure, single points of failure. And recovery without having to go to great extremes. Also, engineers identify the aggregated interface and confirm the link status. So the identifier value for the virtual local area network will also be included. That time I actually got to pause. And it's important that the devices on both ends of the connection support link aggregation in the same way, so that termination may also be important at each of those locations. And systems inherent in the LACP process can also help to handle the out-of-packet order problems, such as scheduling algorithms and defining packet-to-packet activity to keep things working in place as they should. Also, vendor systems provide this protocol, so some of our open source providers can accommodate this implementation of link aggregation. And in general, it helps to standardize how link aggregation happens for more durable Ethernet transmissions. So it's a very important process that we have in our networking. And then we have full duplex and half duplex when we're talking about communication. This is a great video, so please go back and watch this. When we're sending and receiving information, of course, half duplex would mean we're sending one way and it gets received. Full duplex is where it is going back and forth. We're sending and receiving, sending and receiving. Half duplex is it's going in one direction. And we're making sure that it's getting there and that you're able to access what you need to access. So please go back and look at that. And we also go into a CSMA, CD, and so on that I added to this, which is part of the full duplex and half duplex information. So go back and please look at those. Now, let's get into port mirroring. And these are short videos that I have here from Cisco, but port mirroring is used on our network to send a copy, just like when you see yourself in the mirror, that's you, right? A copy of the network packets that we see on one port to a network monitoring connection on another switch port. So we're mirroring that information so that we can monitor that connection. And I do have a great video from good old Professor Messer from the Security Plus, talking about physical port security. So please watch this. It's really good how he explains this. Now, this kind of goes along with what he's talking about, how we configure our violation modes when we're looking at switch ports to protect or restrict or to shut down. In protection mode, we have what's called the sticky feature, right? And the frames that are dropped and the interface continues to function and no log entries are made. We're in protect mode. In restrict mode, those frames get dropped. Excuse me. The interface continues to function log entries are made, and the security violation alert gets sent. In protect mode, it's just doing what it's supposed to, protecting, so we're closing everything down. Restrict mode is now we're going to restrict things. We still want to see information and go from there. And then shutdown mode is where from that port, it's completely disabled. The security violation alert is sent. The default violation mode goes into effect, and the no shutdown command to allow the function comes on. Now, when I'm programming switches, which I do in the Cisco classes with my students at Delaware, we can, in our router, in our switch, we can tell it in command line interface or using the Terraterm terminal to tell the equipment what we want it to do. We can go into no shutdown command to allow functionality. Now we have that functionality, not everybody else does, but we do. So the idea is either do protect mode, restrict mode, shutdown mode, or you can do a combination of these different modes for port configuration. Now, switch looping. Now, switch loops occur when the network switches are connected together in such a way that the network traffic loops around infinitely instead of traversing the hops that are needed to travel from the source to the destination. Remember, we're hopping from router to router to router to router to make our destination using our MAC address, right? So in our core switching, which is our backbone of the infrastructure, because we're using our access switches, right? In our core, we're looking at, okay, normally the traffic goes through, it traverses through, it goes through everything that it needs to, all the different layers of our OSI model or the TCP/IP model to go from one location to the other, and whatever it has to do, how it has to travel to get there. But here you're just like indefinitely looping. It doesn't make its destination. So it can take down your entire network. And it's very difficult to trace back to where it originally originated from. So we're looking at, we've got 4 switches here. We've got a couple laptops, we've got a web server, and you see there is a loop that is continually going around between switch B and C, which is wreaking havoc because the network traffic is not going the way it's supposed to be going. So it's going to make it hard for us as we continue on here, looking at the core and these other switches. We're just in this constant loop of the network traffic that's going on, and we just don't know where it's come from. Is it the laptop here, the laptop here, the laptop here? We're not really sure. So that switch looping creates what is known as the broadcast storm. So again, it could be someone accidentally physically loops an Ethernet cable to 2 ports in the same switch. This is why good cable management helps. Why you see things labeled. When I first went to UF, nothing was labeled. You didn't know what connected to what. It took me lots of time. Parted between all the buildings that I had with nothing labeled. No data ports were labeled on the walls. There was nothing labeled on the actual cables running through the ceiling down to where my switches were and my routers. It was a mess. It was just there. Anyway, which is why I put good cable management helps here. Everything should be labeled so you don't make that mistake. So a loop can also form when the switch is intentionally connected via 2 uplinks to another switch for redundancy if the proper configuration isn't put into place for it to logically connect the way it should, which could create the loop. So the idea is, again, I've told you before, a lot of times the errors that we have occur because of misconfiguration, whether it's in security, whether it's working with the equipment. So you'll see below in this figure, it shows an instance of a loop between switch A and B. And under normal circumstances, broadcast would not flow in a loop because there would be no loop. It would be just straight going from one computer to the other. However, when you introduce this loop between A and B, it causes a broadcast storm, right? The traffic just keeps circulating and duplicating itself until it overwhelms the system and then shuts you down. I'm sorry. The idea is you don't want that to happen. We don't want a broadcast storm. So you have to make sure when you're configuring your ports that you're documenting everything, that you're labeling everything, and that you don't run into these issues. It's not the most common thing, but it does occur. Now, the switch looping fix is the spanning tree protocol, STP. So the gold standard for preventing switching loops is using the spanning tree protocol. It works by creating a group of switches that exchange information via special frames called your bridge protocol data units to create and maintain our loop-free environment. Right? So whenever a loop gets detected, the switches will then share this information with each other, utilizing this bridge protocol data unit information, and select a port implicated in the loop to place into a blocking state based on the lowest cost path metrics. So this effectively logically deactivates whatever links are necessary to keep the network loop free. That's the purpose of it. So here's a physical loop, physical topology. Switch 1, 2, and 3. Now you see these are operating like they should, but switch 2 to switch 3 has created a loop. So something was wrong here. Something was misconfigured here. So here's our logical topology being loop free. We are going from switch 1 to switch 2, or switch 1 to switch 3, not switch 2 to switch 3. We don't need to. When we look at this physical topology, now we've added a 4 switch, right? Looped. We've got switch 1 to switch 2, switch 1 to switch 3, switch 1 to switch 4, switch 4 to switch 3, switch 4 to switch 2. You don't, and switch 4 to 1, switch 2. This creates a problem. The idea, keep it clean. I did not do it this way. Keep it clean. Switch 1, switch 2, switch 1, switch 4, switch 1, switch 3. These all don't need to be communicating with each other. Make this your focal point. And that's why spanning tree makes your life so much easier. Now, when we look at security, your best practices, you should always be changing your default credentials. You should enable the secure shell and disable telnet. You should disable or configure your SNMP, right? Your simple network management protocol, and disable any unused ports. If there's nothing being utilized, disable those ports, because you're leaving yourself vulnerable for somebody listening and port sniffing from the other side of the internet. Add a banner. We use banners. Information that displays, including the version of and operating systems about the services running on a different port or ports of a host server or a system. And you can enable your logging. That way you can follow and monitor what's going on. Now, Professor Messer has a great video, and this is from also the Security Plus, but it pertains to networking, port security. So he goes over port security. Now, we talk a little bit about different things like ARP poisoning, DHCP snooping, things like this. So when we look at our dynamic host control protocol, right, because that's automatically, our addresses are automatically distributed for us. We don't have to manually do our IP addressing provided. So to figure out how DHCP snooping works, we have to catch the working mechanism, right, of DHCP, which stands for Dynamic Host Configuration Protocol. Once it's enabled, the network device without an IP address is going to interact with the DHCP server through 4 stages, right? If it doesn't have one yet, we've got to allocate one. So here's our client going to the server. So this is the discovery stage, because we have discovery, offer stage, request, and acknowledgement. So the DHCP client broadcasts to the DHCP to discover, hey, I'm here. And then the DHCP replies with its offer message. And then the request stage comes in and says, okay, the client broadcasts the DHCP request message, and then the acknowledgement, the ACK, acknowledgement that DHCP server replies and acknowledges now this client. So now we've got ourselves set up, right? That's the norm how it works. Now, when snooping comes in, it's generally classifying these interfaces on the switch into 2 categories. One is trusted and one is untrusted. Those ports are either trusted or untrusted, as shown below. A trusted port is a port or source whose DHCP server messages are trusted. No brainer. An untrusted port is a port from which DHCP server messages are not trusted. I know this seems like, well, okay, that makes sense. But if the DHCP snooping gets initiated, the DHCP offer message can only be sent through the trusted port. Otherwise, it gets dropped. That's the idea. So here's our authorized DHCP server going to our trusted port on the switch. And then here's our rogue DHCP. So it's trying to send this to a port, which is untrusted, right? But it could get a response back. But the idea is it's in the offer stage and the discover that we're looking at. So when we look at the offer, if we go back here, this is the part where we have to be careful to make sure no bad naughties are getting in, because the DHCP replies to the client with an offer message. But if it's coming from an untrusted port, more than likely, if we have things set up and configured properly, the rogue DHCP server, they're not going to get what they want from our interface. They're not going to be able to access this port on this switch. We need for it to communicate, as we've said here, unless the offer message is sent through a trusted port, it gets dropped, right? It gets dropped. Now, address resolution protocol spoofing. This is where I'm pretty sure you probably have heard of man-in-the-middle attacks. They're sitting there in the middle, waiting and watching and monitoring. So ARP spoofing is a form of the man-in-the-middle attack, which the attacker allows the attacker to intercept the traffic from other hosts, right? That's intended for those other hosts. This is accomplished by them sending out crafted ARP packets, which have poison, that poison the ARP cache on the networks. Because remember, the cache is what's storing, so we don't always have to redo every single time we're looking for somebody or we want to send information or share our data. So the cache is, that's why they tell you delete your cookies, empty your cache, delete your history in your browser, that kind of stuff. So by poisoning the ARP caches of the network devices, such as our end hosts like A and B, switches, okay, firewalls on our local area network segment, traffic is then redirected to the attacker's machine. So below is an example. So we have host A and B, we have our ports on our switch, okay? And the host attacker is sitting here. This is 10, 10, 10, 10. This is 10, 10, 10, 20. And he's pretending to be 10, 10, 10, 30 on port 3. He has gotten the capability of intercepting by utilizing these packets that he's poisoned in the cache. Now, if we put up a block for him not to be able to do that, then he wouldn't be able to do that. But that's what they do. They try to find areas where either we haven't configured properly, we're not maintaining or monitoring properly. And the next one is called the dynamic ARP inspection. So we've got dynamic ARP inspection. And this feature in our Microsoft switches, right, they protect the network against the ARP spoofing. So we want to put things into place so that we can remedy these situations. And what they do is the packets on the LAN, they use the information in the snooping table, remember everything has tables, on the switch to validate those packets, those ARP packets. So here's the schmo, right? Here he is. I'm saying I'm this, right? I'm 10.1.1.2 on ARP and I'm MAC-C, right? Well, I'm going to be, right, this is someone, and then I'm going to be ARP 10.1.1.2 saying I'm 10.1.1.1 MAC-C. Here I am, none matching the ARPs in the bit bucket. Okay, so it's not matching either one. The DHCP snooping's been enabled with the dynamic ARP inspection. So using the DHCP snooping binding table of information, the dynamic ARP inspection prevents this from occurring from them getting over here to MAC-B, 10.1.1.2 with the MAC address. Remember, because it's MAC. So by doing so, if you don't have these things in place, he could actually get in to the port and then get in to this device, have access to that particular host. But this is what prevents us from being able to do that. If we don't have something that's matching within our ARP, in our bucket, we've locked it down. So he's not going to be, he's going to try and snoop, do his man in the middle, but he's not going to be able to because we've got dynamic ARP inspection in place. Now, when we look at switch attacks themselves, we look at what's called MAC flooding or MAC spoofing. And what that is it's, and it doesn't matter if it's wired or wireless, it's exploiting flaws in our authentication, looking for flaws in our authentication methods that we utilize. So in layman's terms, MAC spoofing is when someone or something intercepts, okay, and manipulates or otherwise tampers with the control messages between the network device and that unique MAC address that we all have that don't change. That's what the spoofing is. And it doesn't matter if it's wired or wireless, if you're hardwired or if you're using wireless. It's intercepting, looking for those flaws in authentication. That's where this lies, in authentication. And that's what he's looking for. Now, VLAN hopping, there's two things we can do here. With VLAN hopping, we're looking for weaknesses in the configuration of the switches, right? And VLAN hopping is a way for attackers to gain access to confidential information or resources that are on our network. This attack can be used by hackers to gain access to restricted networks and restrictive or sensitive data. Once they get access, and again, a lot of times this comes from authenticating and what permissions we've given people, right? You and I, we wouldn't really have access, even at my workplace, just being a faculty member. I'm not going to really have much access to give them anything that's going to be really worthwhile to them because I don't have any elevated permissions to anything the way we're set up. But if I was a chairperson or something like that, they would be looking for someone like me because now I have more access and authorization. This all rolls together. So a VLAN hopping can attack can occur in two ways. We have what's called double tagging and switch spoofing. In double tagging, this occurs when the attacker adds and modifies tags on our Ethernet frame to allow the sending of packets through any VLAN. And it takes advantage of how many switches have the process tags. The switch spoofing is the process of modifying the MAC address of the device to pose as an authorized switch port and gain access to the target. So this gives you an idea in these images, the double tagging and the switch spoofing. We see the attacker is on VLAN 10, right? The attacker sends double encapsulated 8021Q frames because it's VLAN, right? The switch performs only one level of decapsulizing it, decapsulization, right? Looking at it, decapsulation, to break it down. And only unidirectional traffic is passed. So the attack works even if the trunk ports are set to off. So the first switch strips off the first tag and sends it back out. Because he has sent two, that one gets through to the victim. Now, if he hadn't sent two, this wouldn't happen because there wouldn't be double tagging. It wouldn't be confusing the system and the port. The switch spoofing is an attacker tricks a network switch into believing that it is a legitimate switch, meaning looking for the MAC address, on the network that needs trunking to go from one to the next to get into other areas, right? Auto trunking also allows the rogue station to become a member of all the VLANs. Remember what trunking does? Trunking allows us to communicate with other VLANs. So once this happens, we've given them access to all the other VLANs we have to get that we have set up in our trunking. So that's what's called VLAN hopping. And double tagging and switch spoofing fall into that. Again, double tagging. Most switches will only remove that outer tag and forward the frame to all the native VLAN ports. So when you double that, it's only looking at the one, okay? And that's what it does. It strips off the first and then sends it back out. And then the second one comes in and only works if the trunk has the same, it has to be the same native VLAN as the attacker. We also have spanning tree protocol manipulation. This attack typically is centered on changing the root bridge of layer 2 on your network. by pretending or falsifying those bridge protocol data units. And this causes the spanning tree protocol to have to recalculate and effectively allows the attacker switch to become the root bridge, unfortunately. So this is the bad naughty sitting down and says, I'm going to spoof the root bridge. I'm going to broadcast out to the STP configuration using the BPDU to force an STP to have to recalculate so I can see a variety of frames forwarded from other switches to it. So he gets a lot of information and then he steps in and becomes the root bridge. And so he gets information to all the rest of this. Not cool. All right, so now I'm going to move on to routing. So basically, I didn't do all the basics of the generalities of routing because we've done that already. So I'm going to get into just the routing part of it. We know that it sends the packet to, computer sends a packet to a router. The router then receives the packet and reads the IP address, right? And then it's going to route and forward that packet to a destination. And the process repeats itself. And the final router, wherever it's finally landing, how many hops away it is, that finally is going to send that packet to the destination computer. So here's the computer, here's our data, here's a route. It's going to go to network A, all the way to network Z to get to computer B. And that's pretty much how they work. Now, I have a video on about how an enterprise network works, because I think that's very important. But just as we had in our switching table, we have a routing table. And this is an example of an IPv4 routing table. The main purpose is to help routers make effective routing decisions, making sure you're getting to your quickest point, the quickest path. So when that packet is sent through the router, it's forwarded to a host on another network. And the router consults the routing table to find the IP address of that destination device and the best paths to get there. How many hops do we need? So then the packet is redirected or directed to a neighboring router or the next hop that's listed in the table until it reaches its final destination. So we've got one for IPv4 and IPv6. So it's letting us know we're leaving from one place, going all the way to the next until we actually get there. And so it records all this in the routing table every time we send out data. Now, Professor Messer goes over what's called dynamic routing, which, as you know, is going to be more robust. You really want to go back and look at this so you understand what that is. And then I have about routing protocol characteristics. We've got link state, we've got distance vector, we've got hybrid routing. So please go back and look at those because I don't want to spend a lot of time just blabbing about it. But I'm going to go over some of these things to help you understand how routing, the different ways we route. So open shortest path first. Makes sense. Why wouldn't you open the shortest path first? This is a link state routing protocol that was developed for IP networks. Okay. The shortest path algorithm, the shortest path. And OSPF is what's known as the interior gateway protocol. So there's a lot of abbreviations, acronyms here. So how does it work? Well, the router or the system within the, it's looking for the router or system within the same area to maintain that identical link state database. And each router or system in that area generates what's known as LSAs, link state database, from the link state advertisements that it receives from all other routers or systems in the same area. And the LSAs that self-generates, that it self-generates. So the LSA is a packet that contains information about the neighbors and the path costs. So based on the link state database, each router or system calculates the shortest path spanning tree with itself as the root using the SPF algorithm, meaning the shortest path algorithm. So an example here, here's our backbone. We've got routers 1 through 6, right? Let's see, 5. Well, 5's not going to be included. So we've got router 1 can go to router 2, router 1 to 3, router 1 to 4, and then 4 to 6 because it's in a neighboring area. Router 3 to 6 because it's in a neighboring area here, area 1 and area 2. So it's going to find what's going to be the shortest path within their neighboring areas or the area itself. That's what the open shortest path first is going to be. So the key advantages, compared with what's known as distance vector, because hopefully you've watched Professor Messer before you came to this, distance vector routing protocols such as routing information protocol, OSPF is more suitable for large enterprise internetworks. It's beneficial for something that's in a larger area. And it can recalculate the routes in the shortest amount of time when the network topology makes changes. So also you can divide into an automated or autonomous system into areas that keep area topology separate and decrease the OSPF routing traffic and size of the link state database of each particular area. Also, it provides equal cost multipath routing, so you can duplicate routes to the TC, the transmission control protocol stack, using different network hops. So this is what it looks like when we're talking about the shortest path. This guy here is looking for what's the shortest path for me to get to one of these and then get down here. And this is what it's found as the shortest path in these particular areas, in these neighboring areas. Now, BGP is what it sounds like, Border Gateway Protocol, border. This is kind of like the post office. So it's the postal service of the internet. This relates to email. So when someone drops a letter into a mailbox, right, the post office, the post service processes that piece of mail and chooses the fastest route to deliver that letter or that package to the recipient, right? So similarly, when we look at the Border Gateway Protocol, we're looking at the data via the internet. It's looking for the best available paths to send that data, picking the best route, and meaning the hops between autonomous systems. So this protocol makes the internet work by enabling data routing. So like an example, when a user in Singapore loads a website with origin servers in Argentina, the BGP is the protocol that's going to be used to enable that communication. Sorry. I thought I muted this, but I guess I didn't. I'll mute it now. Okay. So when we're loading that in Singapore, right, that website with origin servers that are located in Argentina, the BGP is going to be the protocol that enables that communication to happen very quickly, very efficiently, and very effectively. So we see, looking here, here's AS300, AS200, AS100. We've got router C, router A, router B. Here's our IP prefix, here's our hops, right? This is going to give us what's the best route for this from A, B, and C. What's going to be, if we're going to be sending information, what's going to be the best way, the Border Gateway Protocol, what's going to be the quickest way as far as when we look at the prefix for B and C and A, right? The next hop, and then the next hop. And I have a video on BGP explaining. Now, sub-interfaces. This divides what's called the parent interface, taking the mom or the dad and cutting it in half or more into two or more virtual interfaces on which you can assign the unique layer 3 parameters, because remember, layer 3, you can do that, such as IP addresses and the dynamic routing protocols. The IP address for each sub-interface should be in a different subnet from any other sub-interface on the parent interface. All right, so here's our router, and we've got using our layer 3 device. We're using our link aggregation group, bundled, right? Our trunking with all our VLANs. So we've got these two here on these two ports. We've got this one here and these guys over here. So we have the ability then to take this and we can use the parent interface and break it into two or more of the virtual interfaces by sub-interfacing. This also leads us to high availability. So I have a video on high availability. Because the point is, when we're routing, is we need quality of service and high availability at all times. so that pretty much it's seamless. Everything that we're doing and everything we're accessing is not noticeable. It shouldn't be. Let's put it that way. Okay, so that's the end of this. There was just so much to that they had and test out as far as their slide stuff, that we were allowed to take and manipulate. And I just didn't want to spend a lot of time, when you talk about routing, there's so many pieces of routing, but it's just general stuff too. I'm honing in on the things that are very important as far as what the router does and how it works, and these kinds of things that we're talking about and the implementation of it, especially for the basic beginning stages of networking, because you're not there yet to get into intermediate and all of that. All right, so that's the end of the presentation. Then I'm going to see you this evening at we'll start at 5:30. I mean, I'll log in at 5:30, 6 o'clock. And then we're going to get into, because this is what we're going to do tonight, is we're going to get into the Frozeware server infrastructure. So we're going to go ahead and do the design tonight. We're going to get it all done. That's the plan. And we've got all the information in the pages here. So please, if you're looking at this ahead of time, please make sure you've looked over or get an idea of all the documentation and what we're doing. We're going to do all of this tonight. So we know that we've got 2 servers. We know that we have 2 PCs, right? Yeah, it's more than 2 PCs. We have more than 2 PCs. First PC, the first server. Yeah, it's been a while. A project meeting. Yeah, 500 client computers, some of which are laptops and tablets. 1 master switch. 3 Windows servers connected to the Frozeware local area virtual switch, 1 DC server, 1 DNS server, 1 VH. So we have different servers here that we have virtualized, right? And we've got documentation per the hardware. So we're going to go over all of this tonight, and then we're going to get this done. All right, so I'm going to get this posted. Stop sharing.